is Wanli Yang here from the ALS. He's going to talk about lithium-ion battery.
So I will talk about specifically how the soft X-ray spectroscopy at the ALS could, please wait, could really provide very useful information on optimizing a material used in lithium-ion batteries. So the way to do that is really to use the soft X-ray spectroscopy to measure some very important electronic states. And you measure all different kinds of electronic states. The reason I call it key electronic state is those are particular electronic states, and they are relevant to the battery performance. By measuring those, you can get a very detailed and very useful information on what is the next step to optimize this material. So what you are looking at on the screen right now is when you have a cathode, battery cathode material, it's a lithium iron phosphate. People expect that to be the next generation new cathode material. When you charge this material, essentially when you charge it, you pull out the lithium from this material, and this is what you will see by using soft X-ray spectroscopy. When you pull the lithium out, you will see the spectrum evolves vividly from these red color ones to these dark purple ones. And the evolution of this overall spectrum tells you a lot of things. The valency is the most obvious, of course, and then those detailed structure tells you the lattice distortion, very local lattice distortion during this charge and discharge process, and detailed other things tells you the phase transformation. When you have lithium in and out, you have lithium phase or non-lithium phase, how these two phases evolve and transform. You can get all this information relevant to the battery performance with the soft X-ray spectroscopy. Because I tucked this a little because I'm not going to discuss this, but you're welcome to join our workshop. I think Xiaosong will discuss the details on this material. What happened is on this booklet, the title of my talk is actually the title of our workshop. So easy for you to find it. I will go through very quickly on what is the spectroscopy we are really using, and then I will jump into the battery. So when you shoot a soft X-ray photon onto a material, especially low-Z material, what you have is if you tune the incident photon energy to have this photon matching this core level electron up to this is the lowest unoccupied state, or we call it conduction band. So when you tune this photon energy matching this, you will get an absorption peak. This is the way how you detect those unoccupied conduction states. And to measure that, you have two different channels. One is after you generate this core hole, all those high energy level electrons, so the energy level is like a gravity of the electron, they will all jump or drop down onto this core hole. And by measuring this energy release through the origin electron, you can get the total number of core hole. That tells you how much your X-ray could be absorbed. And of course, you probably, most of you know there is another more important channel, which is when you decay, you just have the photon emitted through this energy release. And by measuring this photon energy, it actually tells you the energy between this and that, all different occupied states. So in combination, if you measure how much this is generated to the unoccupied states, the absorption tells you the the unoccupied conduction band, which is the absorption. And when you measure the decay of the photon, what is the energy of this decay photon coming out? That's the so-called X-ray emission. It actually tells you the occupied valence band states. And the combination over here is the band gap. I am very sure this diagram, you can see them, you can see it very popular. It was drawn many years ago by Jinghua at the ALS. He's sitting right there. So batteries, why we use an expensive synchrotron facility to study batteries. So when you look at the public media, especially in the last 1 or 2 years, you will see from the national-wide to the local San Francisco, all the lab, everywhere, that they are talking about a rush on developing a high-performance battery. So the reason is energy storage is not only important for the green energy storage, that's a great scale, it's actually another story. The other immediate thing is we want to push forward to get rid, well, there's no way to get rid of or to minimize this fossil fuel use, especially in transport vehicles. So the electric vehicle at this moment, there is no mature battery technology really to push everyone go out and buy an electric vehicle. There's safety concern, cost effect, performance, capacity, and the power. So all those factors limit. This limit on the battery limits the commercialization of the popularized electric vehicle. So when you look at the battery you're using right now, if you ever, well, you don't open up your iPad, but you can find it easily on Google. So if you open up your iPad or Mac Air, those portable electronics, when you open it up, it's dominated by the battery. This is the whole back side of the Mac Air. The battery cells are here, and those are battery cell, and this is the size of Chevy Volts. So it takes 2 guys on a car transport in, and this is actually not a plug-in vehicle. The Prius is a hybrid vehicle. The battery size takes almost most of your trunk size. It's a huge battery sitting underneath it. So the volumetric energy density or capacity is one of the concerns, and the other thing is the safety. So the synchrotron really works by detecting the fundamental physics on how this battery works, and with the hope this fundamental information could tell you what is your next step to optimize the material. So when we look at the lithium-ion battery, I guess most of us have the fundamental idea on how this works. When you use a lithium-ion battery, it's a discharge mode. You have the lithium migrate from the anode to the cathode, and then your electron goes outside. That's how you make it work. Well, with this, you can already have an idea. So when you drive the electron or lithium from the anode to the cathode, the energy gain you get is actually the potential, the chemical potential between this anode and the cathode. This chemical potential difference gives you the so-called over-circuit voltage. The voltage is very important in a battery because it determines the power of your battery. In other words, if you use this battery in your electric vehicle, it tells you, it determines how fast you can speed up your engine, how fast you can speed up your car so you can merge into your freeway safely. So this voltage is determined by this chemical potential of the anode and the cathode. And in the meantime, you are limited by this so-called electrolyte hallmark. It's the lowest unoccupied molecular orbital and the highest occupied molecular orbital. So if you have this energy level sitting above that, you will reduce the electrolyte, or if this is lower than that, you will oxidize the electrolyte. So although you want this voltage to be as high as possible, you cannot go above this limit. The sad thing is most of the battery, or I can say all of the lithium-ion batteries you're using right now, they all have this problem, meaning either your anode or your cathode will decompose your electrolytes through either reducing or oxidize the electrolyte. And this is what you are using right now in your laptop or iPhone. So what you have is your anode energy level, it does sit above this electrolyte Loomer level. However, what happened is on this surface of the anode, there is a very special interface forming. It's called solid electrolyte interface, the SEI. And the forming of this SEI is critical. It actually protects the electrolyte from being reduced too much so your whole battery collapses. So once you form this SEI, your whole battery is stabilized. So at this moment, controlling or to understand control this SEI layer in the lithium-ion battery is one of the major topics in this battery research. And so, of course, the ideal case is if you have two materials with anode and a cathode, if you can really control this SEI layer on both, you will reach the very high voltage with a safe operation. This is the ideal case. So the soft X-ray, I think I finished my introduction on the lithium-ion battery. The soft X-ray really could tell you on many aspects all those information. So this is a SEI sample we detected using the soft X-ray absorption by Ruimin Qiao in our group. So what happened is on two anode surface, these two anode surface has very different performance. Well, the red color surface, they have a very stable cycling performance, while the blue one is very bad. So using the soft X-ray spectroscopy, what you can see is actually on one of the surface, you actually form from the beginning a pretty okay layer, a surface layer, while the other one, the electrode itself has a catalytic type of performance to decompose this SEI layer and form another type of SEI. And this tells you a little direction on what is the next step, what is the chemical species you are shooting for to form this SEI, and also you need to pay attention on the electrode itself, although the SEI is normally considered just reduce of this electrolyte, but it's clearly affected by the electrode too. And the other example I will just talk about very quickly is on this anode material, I was talking about the lumer or the anode is sitting up right here. So with the X-ray absorption, the edge of the absorption edge really tells you the change of these lumer states. And when you look at the material, three different materials used in this anode, and what you see is some of the material has a particular state sitting at very low energy. Those low energy turned out to be very good because this is the band edge on the lumer, and when you have a lower energy, the electron under this reducing environment will tend to jump onto this lower energy state. And that will improve the overall performance of the anode by 7 to 8 times. And in the paper we showed cycling for almost 700 cycles. And this is a sort of a successful case. So my talk is, after this, my talk will really focus on the transition metal oxide-based cathode materials. So the cathode material is much more complicated. The reason is they typically have multiple type of elements, and they are highly correlated systems in physics. So, and when you look at the cathode materials right now, people are studying, and also some of the material like these two are commercialized, partially commercialized. They are all transition metal oxide or phosphate materials. And what you are hoping is when you charge and discharge, you will change a redox of this transition metal valence. However, you keep all the other things not changing much. So all those transition metal oxide materials, they all have sort of like a basic structure. And when you have the lithium goes in and out, the lithium takes a particular space, either layered or 1D chain, or this is actually a 3D type of diffusion channels. So I will talk mainly about this lithium iron phosphate, which is considered to be the safest material at this moment to be used in the electric vehicle. However, it is very interesting because this material is the only material by this moment has only a 1D channel lithium diffusion, which is typically considered to be very bad material for the lithium-ion battery. And then if I have time, I will talk about the spinel material a little bit. The spinel manganese material is almost a solo concern now by the major industry, Nissan, GM, Ford, and So the spinel material, they consider to be the most promising materials. Okay, so we talk about rational guidelines. So, and then we want to take a look at the history of this battery cathode. In the history of this battery cathode development, in the field of battery, I am very sure everybody in that battery field knows Professor John Goodenough. The reason is he invented not only the first generation lithium cobalt oxide cathode, he is also the person invented the lithium iron phosphate. So in a book chapter he wrote, a 2002 book he wrote, there is a very important concept in the designing the cathode. So designing something, although most of the material development is truly based on trial and error. However, in the history of battery, designing of something is feasible. So he talks about particular redox level pinning. This idea is very important. And he said because from this consideration, before that it's mainly sulfate material to be used in the cathode, he said, following these considerations, we need to go to transition metal oxide. And I think most of us knows what is the result of this switch. The result is what you are using right now in your laptop and iPhone. And this, he was actually inspired by an undergraduate thesis on the lithium nickel oxide, and he invented nickel cobalt oxide. And that nickel cobalt oxide is what we are all have been using in the last 2 or 3 decades until now. That's the lithium cobalt oxide. So what is this redox coupling? So this redox level pinning is actually a little fundamental physics. However, it's actually fairly easy to understand. If you look at the free ion, energy level, your oxygen -1 or -2 is always sitting above your vacuum level. That's why it tends to become oxygen 2-. It's the so-called negative electron affinity. And your transition metal with different valency will sit below the vacuum level. When you bring them into an ionic system, all those energy level will be adjusted by this ionic energy. We call it Madelung energy. And after you alternate all those original energy levels by this Madelung energy, you will form all different kind of bands. And in these bands, typically you have those anion, in this case oxygen 2p if it's an oxide, oxygen p band, and the transition metal 3b bands. Those are the bands really determines the property of your material because they are the most closest these are closest levels to the Fermi level, and Fermi level is the most important physical energy level to determine the property of the material. So the relative energy position of this 3D state to this anion oxygen 2p state, this relative energy position is what Goodenough was talking about on this redox level. And this redox level, or this, okay, I'm getting there. So why this redox level or this energy alignment diagram is very important. This is associated with a so-called Zanang-Swatsky-Allen diagram in fundamental physics. So you have the D level sitting above or below your P determines 2 different kinds of insulators. If I would translate this diagram into a battery cathode, what you have is you always have a redox sort of pinning on top of this B state. You always have a little bit there. That's from the covalency between the P and the D. However, it determined by where this D state is way below it or is above it. It determines the majority of the character close to the energy level is majority P or majority D. If it's majority D, that's what you are hoping when you have charge and discharge, you have electron holes into this cathode material. You are all changing this transition metal valence instead of changing anything else. However, if this is majority P, you will introduce this hole into your oxygen or sulfur, those anions. The result is you form this oxygen 1 minus, it will release oxygen into the flammable electrolyte. So when you inject oxygen into your flammable electrolyte into a car battery, it will explode. So that's why this diagram of that actually tells you how safe you could operate a battery. And the other thing I didn't talk about is how stable you can achieve this D state, high valence D state determines your voltage of your battery too. So then our first problem is really whether we can use the soft X-ray to really get this diagram out experimentally. And this is a set of transition metal B-fluoride. We choose it because it's very ionic state, the same as the battery systems. It's very ionic states. And what we see is this is the emission and this is the absorption. We see a bunch of those hybridization features between the oxygen P and the D. By making use of these hybridization features, we are able to align the transition metal 3D and the anion P. You can see that all the 3D is sort of crossing this F2P level from the top to the bottom. That actually does map out the Danang-Sawatsky-Allen diagram. And then if we use the same technique on the lithium iron phosphate, what we see is this is a series of different lithiated lithium iron phosphate. You will see there are two so-called isospastic points in spectroscopy, meaning there is one state, two state, another state here. And when you align this iron 3D to that oxygen 2P through this hybridization feature, you will get an alignment of this 3D and 2P, and this is the result. So the result shows when you go with lithium getting into this lithium iron phosphate system, what you have is when you pull all the lithium out, this is a suspicious status where you have the safety problem. In this lithium iron phosphate, you do have the D sitting together with the P. And when you pull the lithium in, what you have is you will have majority of this pushed down. However, there is another extra electron sitting well on top of this P state. And this is also fundamentally interesting because the 3D level has 5 orbitals. If you remember the Pauli law, you have 5 orbitals, and now you have 5 electrons. All your electrons have to be spinning one direction, like spinning up. So if you now introduce one more electron going in, it has to be the opposite. That's a spin down. So the spin up and spin down, they got a chance to get onto one side. That's how you separate this out by repel these two groups of electrons with different spins. And so what I mean is this material or this study not only tells you what are the safety concern on this electronic structure point of view, it also gives you a very nice playground for the fundamental physics. So I think I will conclude. So I was talking about so-called key electronic states. What do I mean, key electronic states? So what we want to say is really the state that's relevant to the battery performance. By measuring this battery performance like a particular state, you can expect this state is associated with a particular structure or polymer functional group or a particular factor of this material. It tells you your next step to optimize this material. You should either optimize this or to keep it. So it does provide you a sort of rational guidelines for the next step optimization. At this moment, I cannot expose too much on the cathode. The anode part is published. But I can almost assure you at this time, you will very soon hear a good news on the cathode part, on really improving the performance on the cathode part. So I would like to thank our postdocs and students working with me. Without them, I have no way to work on science, even I don't sleep at all. So they are So they are Paul and Xiaosong and Ruimin. So they work on individual project, lithium iron phosphate, the DSA diagram, and the manganese, and Ruimin work on the SEI and various things. And we have, at the ALS, all our colleagues, we talk constantly on discussing all different topics. And Zahid has been always supporting us with both financially and scientifically. And our 2 years after we started this, our collaborators have been internationally expanded. The data I've shown today are mainly the local collaborators with our ETB groups of people. We talk to them directly, and that's the only way how you can work out with material optimization, meaning you measure the spectroscopy, you feed this specific information back to them, and then we discuss the next step to optimize the material. These are all very important. And of course, our theoreticians always helps us to finalize our understanding on the spectroscopy to connect it to this battery performance. Thanks.